Hi everyone, my name is Nikunj and I'm a final year computer science undergrad from India. I work for the Stellar Group and contribute to the HPX library, wherein I work mostly on the resiliency APIs and executors. And in today's talk, I'm going to present you a way of writing composable APIs using executors. And as a case study, I will use the resiliency APIs that I've been writing. So before I begin with the talk, I want to mention a couple of things. First, is that this is not a basic concurrency and parallelism talk. So I will use concepts like futures and C++17 parallel algorithms without really explaining them much. And secondly, since HPX has implementation for both parallelism TS and concurrency TS, I will use the future concept defined in the concurrency TS. And the only thing that you need to know about it is that it allows you to add continuations. So things like dot 10 to the future is a continuation. So for the outline of my talk, I will begin with what HPX is, followed by a case study of software resilience for high performance computing. And based on this software resilience, I'll bring the point for the need of executors in such a scenario. And finally, I'll explain you the HPX executor architecture and end it on a broader perspective of composability. So HPX is a general purpose runtime system for applications of any scale. So that just means that you can run HPX on something like a Raspberry Pi. You could run HPX on your laptop computer, or you could run HPX on a high performance supercomputer. It runs everywhere. Next is the standards. HPX is a standards conforming API. So anything implemented within the standards has been re-implemented in HPX. Now, we're not fan of re-implementing things. The reason we do re-implement is because first we have our own threading subsystem. So that's a lightweight threading subsystem, and to allow for the use of those threads and concurrency defined by those threads, we need to implement our own futures, we need to implement our own threads, and so on. And the second reason that we need these APIs is because the standards API cannot be sent over to remote localities. Since HPX supports parallel and distributed operations, we need to make sure that these functions are serializable, and we can have implementations such that we can use these functions to invoke tasks on distributed end. And since HPX has a really lightweight threading system, we support full asynchronous code, and that can use millions of threads at a time. And similarly, we have similar syntax and semantics for local and remote operations. So as I said, we re-implemented things in HPX, and the reason why we re-implemented is because we wanted to conform to the standards API, and also we wanted to support distributed APIs. So we use the same APIs for both local and remote, and you'll see why we do that in a later stage. HPX makes concurrency manageable with data flow and future-based synchronizations. So futures and data flow are the basic building blocks of HPX. And HPX boasts itself as a task-based parallel model. So we define things in terms of tasks, and futures and data flow helps us do that. Now, a data flow is a function that waits on a set of futures, a few futures, and then once all of those futures are ready, it invokes the kernel that is given to the data flow. And finally, HPX is an open source project under the Boost license, so you can literally do anything that you want with it. Now, as I said, HPX is a task-based parallel system. What happens is you start with a single task, you invoke multiple tasks. Now, these tasks can have dependencies, and the overall flow of the program depends on these dependencies and these executions, and the whole structure, therefore, can be categorized as a task-based system. And if you want to know more about HPX and how we do things in parallel, there's a really good talk on HPX and parallelism. That's called the Parallelism in Modern C++, given by Professor Hartmut Kaiser at CppCon 2016. Now let's shift to the idea for resiliency. And the first thing is we're entering the realm of exascale computing. So that's 10 to the power 18 floating point operations per second. And that's a lot of operations. And if you see, if you want such a scale of operations, you will need big machines. And as we've always heard from Spider-Man, big machines come with big machines comes big responsibilities. And what happens now all of a sudden is we enter into the age of silent data corruptions. Now, silent data corruptions are errors that arise from unexpected aberrations in data or compute. And these aberrations, these corruptions are not detected either by your hardware nor by your software. So for example, it can transmit itself through the hardware, through the operating system, and can actually enter into your program. So as a very simple example, now you would think that a machine is always right, but sometimes it could actually compute 1 plus 1 as 3. Now, as silly, as stupid as it sounds, it can actually be true. The thing is, such silent data corruptions have abysmally low probability of occurrence. So for all practical reasons, you will not experience such a situation on a personal laptop or a personal desktop or even a cluster that does not have a lot of processors. But literally, what do you do when you have a ton of processors? And as I said, with big machines, you will have a lot of processors, you will have a lot of computing power. So what do you do then? And the thing is, should you care about silent data corruptions? And my answer to that would be it depends. What does it depend on? Here's the question: does the application run on a million runs on millions of threads for a long time? So that means that does your application takes up the whole supercomputer, and does it run for weeks or months at end? And if your answer is no to that, then I'd say don't bother add resiliency, because adding resiliency adds both overheads. Well, even though it's really low, but it still does add overheads. And the second thing is with resiliency, with such, if you have an application that does not use millions of threads and does not run simulations for a really long time, what happens really is the practical impact of such silent data corruptions are none. So you will actually never witness such a scenario ever. But what if the answer is yes to that question? So here's a counter question: is the application mission critical? And the question here is broadly about, like, let's say you have an astrophysics application. I don't know, maybe it simulates a black hole, it simulates a binary star, it does something very crucial, and the results of these simulations are then given to scientists who have to prove scientific theories or something like that. Are these the implications of the simulations that you're running? If the answer to it is no, and you can actually have results that can vary slightly, then again, don't bother adding resiliency. But if the answer is yes, then I'd say add resilience and save everyone from explaining weird results. Because sometimes you will experience weird results, and I don't know, maybe your black hole simulation all of a sudden comes up with the speed of light that's not equivalent to what we have to the date. So what do you do then? You will have to explain the speed of light being something different, and that is something weird. That is something not accurate based on the simulation. But you're getting those results, and you will have to explain those results. So in such a scenario, I would highly recommend you to add resilience and save yourself from explaining weird results. And now that we've come up to the point of adding resilience, let's talk about HPX's implementation. Now, we assume a few things to begin with. First is that since HPX is a task-based runtime system, we do not expect you to change global state changes using global variables. What that means is you do not use standard atomic, you do not use conditional variables, you do not use any global primitives to synchronize between two running tasks. What we indeed want you to do is to use built-in constructs like channels. Channels are a way to communicate between tasks, and that is essentially what we're promoting here. Because if you use global variables to do things while you add resiliency, you've already changed the global state. So you'll really have to roll back to that state again to actually have the same to have the correct output in the end. So state changes using global variables is a strict no-no. The second thing is a task do not change the input data parameters. And this is mostly based on a performance standpoint, because if you were to save input data parameters, then that's a memory operations. And memory operations are expensive and will definitely cause performance bottlenecks. So we do not want to do that. We want to make sure that the input data parameters are not changed. And this is something inherent to the HPC application kernels. So a lot of HPC application kernels that you will see do not really change the input data parameters, or the data parameters that they change are the ones that correspond to the output data. And since we're rewriting those output data ourselves, it doesn't really matter to us. And based on, there are a few other assumptions that you can go through, by the way. So that's defined in the paper that I've linked to right here, that we submitted and got accepted last year at the Supercomputing Conference. And based on the assumptions that I just told, task boundary is an ideal position to add resilience. And the reason why I tell you that is, let's assume a task 1, right? And this task post completion will give you a result and will invoke a next task, task 2. This result could be incorrect. So what do you do now? Well, there's a simple way. You can take this result and you can add sort of checks, and you can make sure that the results are credible and can be sent to the next task. So when you have such a check mechanism between tasks, task boundary actually becomes a really good position to add resilience in your code. And based on this, task replay and task replicate become really intuitive. And what in the future slides, you will know why I said that. So for example, let's take a task replay, for example. So that's async replay in HPX. And what happens there is you start with the task A. You check if there's any exception in that task. If there are any exceptions, then you rerun the task recursively as long as you have the replay options. And if there are no exceptions, you go ahead and you run the next task. And since it's very easy to think of it as a recursive call, that's how we implement it in HPX as well. Well, we make use of an async replay helper, for example, over here, and we simply recursively call this replay helper. So let's take a look on how async replay helper can be defined. So what we do here is we simply invoke the task using the async function, and the future that we get, we attach a continuation to it. And the part over here that you see exception detection is done in this continuation itself. So once this task has completed execution, the internal kernel is then executed. And all we check is if this future received any exception. Now, if it did, then we check if we have more replay options. And if we do have replay options, we simply recursively call the replay helper again. But let's say if we do not experience any exception, what do we do then? Well, in those cases, we simply return the future, the value that we got to the next task. And that's exactly what you see over here as well. That's easy, that's intuitive, and that works. Next is async replicate. It's again very intuitive method wherein what you do is you take a task A, you replicate it up to n times, and you get results from all of these tasks. And once you get the result, you simply send the result to task B. Now, again, this is dependent on exception handling. So what we do is we simply send in the result that the first result that did not have any exceptions. And the implementation itself is again very simple. All you do this time is instead of invoking a single future, we start with a vector of futures. And we simply push back to this vector, the function, the task itself. And this time we make use of data flow. So as I said in the previous slide, the most basic building blocks of HPX are futures and data flow. What a data flow does is it waits on a set of futures. Over here, that set is a vector of futures. And once all of these results have been executed, the futures within these vectors, this internal kernel is then executed. And all we do now is we take these results and one by one we check if the result has an exception. If it has any exception, we simply attach the exception pointer to it, and if none of the tasks actually computed, we send them, we rethrow the error. But if any of the tasks actually went ahead and went to completion, we simply return the result of that task. And at this point, you would think that, well, exception handling might not be the only scenario. For example, let's say, as I told, 1 plus 1 equals 3. If it gets into your application, there won't be any exceptions. So what do you do then? In those scenarios, what we have to do is we need to have algorithm-based fault tolerance. And we can have that using validation functions. So essentially, we'll have some sort of validation functions at the end of the computation. And these validation functions will see if the result is actually correct or not. And based on replicate, since I said that we simply return the first result that did not throw any exception, we can have scenarios wherein, let's say, more than one task did not throw any exceptions. And simply based on that, we will have multiple results now all of a sudden. What do we do then? And it could be simply the case that the first result that we got actually was incorrect and actually went through the whole operating system hardware and got into the application. In those scenarios, we can have consensus, and we can have consensus through voting functions. Similarly, as I described with algorithm-based fault tolerance, we can have validation functions to check if the results that was computed by the task is indeed correct. And another thing is we can have a function that does both of these things. So it would first validate if the results are correct, and if more than one result validates, we can have a consensus over those functions. Now, other than that, we will have to see the scenario of handling distributed software resilience as well. Over here, since the last time we simply took a function or a function pointer, what really happens is that you cannot send them over the wire to another remote locality. In such a situation, you need serializable entities. In HPX, we call them actions. With serializable entities, what happens is these addresses are mapped such that you can actually invoke it from one locality to the other. The reason why you cannot send in a function pointer is due to the address-based randomization that happens within the operating system. So a function may have an address, let's say A, on locality number 1, might not have the same location on, let's say, locality number 2. The next thing that we require with respect to handling distributed software resilience is to know which locations we really want to invoke these tasks on. And it's actually really easy to implement these variations as well. So like I said, with validation, all we need to do is, instead of simply sending the result, we simply send in the result to a validation function. And if the result is invalid, we again invoke the task A. But if the result is valid, we go ahead and we return the result to the task B. In terms of implementation, it's not very different. All we do is, instead of simply returning the result, we first we get the result and we invoke the result with the predicate. Over here, that's the validation function. And if that works out fine, we simply return the result. If it does not work out fine, we recursively call the replay helper again. Similarly, with, let's say, if we have the scenario of async replicate vote, what do we do there? Well, we have a bunch of results this time. So all we do is we send it through a voting function, and this voting function will then compute a result based on that function and send it to the next task. In terms of implementation, again, it's not very different. All we need to know now is we need to have another vector of results that keeps the results of exceptionless results. So what happens is, in the previous case, we had a vector of future that run all of these tasks. Now we need to know the results that had exceptionless results, and that's what we do. We push the result back to the exceptionless results, and once we have a few results, we invoke the voting function. But what if, let's say, if none of the results actually went ahead and all of these tasks actually had exceptions? In those cases, we simply again take the pointer to the exception and simply rethrow the exception again. Moving from async replicate vote to a distributed scenario, that's again not a very difficult situation to handle. All that happens now is we have replication, but this time we have replication on different locality. So task A may be invoked on locality number 1, the replicates may be then invoked on locality number 2 and 3. And these results come back on the first locality. And again, the rest of the things are again exactly the same. Do voting and send the result to the next task. In terms of implementation, all we need to change is we need to change the way of handling vector of futures, right? And again, invoking tasks, since I said HPX has similar semantics for both local and remote operations. This time, the only difference to invoke things on a remote locality is to send in an action and tell it which locality you want to invoke it on. And that's the only change you need to do going from the local only version to a distributed version. And based on this, you can actually implement all the other variations that I talked about in the implementation variation slide. And these are actually very similar. The way we implement it in HPX is a bit more fancy, wherein we have a single interface to do all of this. So this way we actually avoid doing a lot of copy and writing a lot of redundant code. But the overall principle and the idea remains exactly the same as I show in this code. And based on this, we did some performance analysis. We wanted to check if there are any overheads or not of using such a principle. And from the slides, if you see the overheads of adding replay and replicate, even if they go on and replicate up to n times and they replay up to n times, the overhead is still based on the invocation of n futures. So instead of invoking a single future, you're now invoking n futures this time. So the overall overhead that we really think, the implementation overhead that is based on the number of futures that you're actually replaying or replicating. Other than that, the overheads come from the voting function and the validation function. So for example, we did a test on 1D stencil local, and a kernel, a very basic kernel of a 1D stencil looks similar to the code in the right, wherein we loop over a few time steps, and in each time step, we do an array operation, for example, the one that we do here. And based on that, the version with the replay validate case has very low overheads. Now, the overheads that you see, the minimal overheads that you see, do not really come from the implementation overhead itself. They come from the validation function. Since we need to add checksums to validate the result, the overheads are not as minimal as you would think. It adds up about 2 to 3 seconds of time. But 2 to 3 seconds for a 40-second execution time is not much. So overheads overall are pretty much minimal, I would say. And we see the same scenario when we inject artificial errors into the code. So when we add artificial errors to the code, we see that the overall execution times do not increase much. And even at the error percentage of 6%, which by the way is a lot and will never happen. And if that happens, your machine has already died, you should simply move that out. But let's say, assuming even if you have 6% errors, even then a replay will not take a lot of time. It would take about 16% more time than usual and do the work. And it's much better than replaying the whole application again, especially when the simulation that you're running runs for months at end, for example. When we go to distributed, again, we have a similar scenario. We do see some overheads close to 4 or 5 seconds, and that's because of two reasons. One, we should remember that validation functions itself takes its own time. And secondly, when you go from local only to a distributed version, network latencies are a thing. And over here, what we see are a mix of both of these options. And that's why we see close to 4 or 5 seconds worth of extra time. But as I said, 10% execution time or 8 to 10% more execution time is nothing compared to executing the whole application again based on a weird result that you receive. These overheads are overall minimum. And we were really happy with the results as well. And based on this, we thought, if the overheads are really low, why not use it everywhere? And we were like, yes, we should actually use it everywhere. Why not? And here's the problem. So consider the case of async. If you have async that takes a function and a bunch of arguments, it's really easy to convert it into an async replay with an additional argument with the number of replays, the same function, and a bunch of arguments. But what do you do when you have, let's say, an algorithm that takes a bunch of arguments? You could argue that you can wrap it around async replay and again add an additional argument of n, that is the replay, the number of replays, and provide the algorithm and the arguments to the async replay. But I would object to that. I would say that it's not readable because the resiliency, the point of adding resiliency is to ensure that it's a property of an algorithm and not an algorithm itself. Furthermore, if you see, if you want to add resiliency across your application, you will actually end up having a bunch of async replay, replicate, and other variations all throughout your code, and it would be really a messed up code in terms of readability. But I'd still give it a pass that if you really want to do it, you can do it this way. What do you do for each? If you have a bulk execution, something like a for each that takes a range and a function, what do you do that? How do you convert it? Now, if you argue that you can wrap it around async replay, I would object. And this time, I would not object because of readability reasons. I would object because of performance reasons, because you're actually invoking unnecessary number of futures. And since it's a bulk execution policy, you will actually have way too many unnecessary futures that will cause both contention in your program and performance bottlenecks. So you can't really wrap it around and call it a day in this case, because you're actually having performance bottlenecks in such a scenario. And that's where executors come into picture. Executors are modular components for creating execution. Now, this is a very brief statement and a brief summary of what executors are. Essentially, what executors does is it works on an execution resource. And based on that execution resource, it provides you an abstraction to run a function on that execution resource. In terms of code, what happens is, let's consider an algorithm, some algorithm that takes input range and an output range and does some work on it. If you want it to support executors, all you need to do is you need to add an additional executor argument. And instead of doing some work directly into the algorithm, you pass it to the execute method of that executor. And that executor would take care of executing that work in that execution resource. And similarly, if you have an executor-aware algorithm, all you need to do is you need to call the underlying algorithm and pass the executor to that algorithm. And somewhere within that algorithm, we'll have a similar effect that we see over here, wherein it calls the execute method and passes some work to it. So this way, executors create a neat abstraction, and it actually solves our purpose. Let's see how it actually solves our purpose. Consider the case of HPX async. All we need to do now is we need to pass an executor to that async, and we will have the property of resilience, because this resilient executor will ensure that it does the replay or the replicate, and it gives it the property overall. Similarly, if we have an algorithm that takes a bunch of arguments, all we need to do now is we need to provide it an executor to that algorithm. And within that algorithm, you could use a similar property as described in the previous slide, wherein you call the execute method and you pass in those arguments, that algorithm itself, to that execute method. And this, by the way, is much more readable, because now executors, the resiliency property is a property of that algorithm. Now it is no longer an independent property, but it's a property of that algorithm. And that is essentially what we're aiming for over here. Similarly, if you have a for each, a bulk policy, essentially, if you have bulk execution, then what we need to do is we need to simply pass in the executor to the execution policy over here, that is the HPX execution part. So this time you will not create any unnecessary futures, because it is part of the policy itself. Since the policy goes on to the executor, it is the executor that creates the future for the bulk execution. So there are no unnecessary or overheads based on the unnecessary futures that we have. And this way we have both readable and composable APIs. We say composable because you can pass the executor to any of the methods, and you can have the property of resilience everywhere, as long as the algorithm supports it, that is. And the way we implement it in HPX, we need to go through the HPX architecture first. And the HPX architecture is based on on quite an old version of executors. That's the P0443R4. The current day version, that is the R14, works on senders and receivers. The changes there are a few, but it's overall the implementation details that changes, and certain features such as lazy execution and exception handling that gets into the picture with R14. The overall concept of executors still remain the same, and since we're more concerned with how the user would use the executors, it really doesn't matter if we're considering the R14 version or the R4 version. So based on that, HPX executors. So an executor in HPX will have one or more functions of post, sync, execute, and so on. Essentially, what every function does has a different meaning. For example, post is a fire and forget method. So you in post, all you do is you pass in a function in executes, but you do not really want the result back. Hence, a fire and forget version. With sync execute, it's analogous to std invoke, wherein you invoke a function, you want the result back, and you want it to be blocking. With async execute, it's analogous to something like std async. You give it a function, you give it a bunch of argument, and it's a non-blocking call. So it will return a future instead. Now we need to understand that I'm using the term analogous. So we're not essentially using the std invoke or std async underneath the implementation. It's basically to make you understand how things would work if it were to compare with something else within the C++ standards. With bulk async execute, it's for bulk policies. So essentially, it's nothing but async execute, but in bulk this time. And similarly, then execute is something that comes from the concurrency TS. Since I said we can attach continuations to a future, we need a way to pass that information to executors itself. The way we do it is through then execute. And if an executor has a then execute method, it supports the dot then function on the future. Similarly, bulk then execute is just a bulk version of then execute. Now, since I said that we allow executors to have one or more of these member functions, we will need a way to actually call these functions, because if we have one or more than one function and we have a bunch of executors, that would lead to compile time issues. So the way we handle it is through customization point objects. So with respect to every member functions that we have in the executor class, we define a customization point object. So a post customization point object takes an executor and calls the post function of the executor. And since we now have customization point objects and executors, we need to make sure we need to glue them together. And the way we do it is through executor categories. And based on the executor category, we have defined 3 categories. So the executor categories are based on the fact that if it returns a result or not. So for example, a one-way executor has no channels to return a result. It is majorly used for functions like post, wherein you really do not care about the result. You only need to execute it. With two-way and bulk two-way executors, we want a channel to return a result. And as the name suggests, two-way executor will be used for something like sync execute or async execute or then execute. And the bulk two-way executor will be used for the bulk versions. As an example, let's take what happens in the backend when you have an HPX async call that takes an executor, a function, and a bunch of arguments. What really happens is it calls the async dispatch underneath and passes the executor as a template parameter. Now, as I said, we glue them together using the executor categories, and that's what we do here. We use this to enable if to have to make sure that the executor that we are providing is either a one-way executor or a two-way executor. And based on that, we ensure that we call the async execute only if that executor is a one-way executor or a two-way executor. Now, within the async execute function, we call the CPO calls the member function of the executor itself. So this async execute method, it's the CPO that I described in the previous slide that takes in the executor, the function, and the arguments of the function, and it essentially calls the executor's async execute method. And based on that, we can actually implement resilience versions of the executor. Now, all we need to do is we need to handle two basic cases. One is to have a two-way execution policy with async execute, and the other one is to handle bulk two-way execute for the bulk execution policies. The way we handle the replay executor is very simple. We do not create a new executor that works on thread pool. All we do is we take a base executor. Now, this base executor has to provide two guarantees. One is that it needs to have async execute and bulk async execute as well, since we're relying on those two functions in a replay executor. So we need to have that in the base executor as well. And the other thing that we're relying on is to have a support to the async replay validate to take a base executor, to take an executor and do things. And as I showed in the previous slides with some algorithm, if you want to support an algorithm with an executor, all you need to do is you need to add an additional argument of the executor and just call the async execute method within the function to make things work. Essentially, that's what's happening underneath the async replay validate implementation as well. Since async replay validate underneath calls the async method within HPX and then attaches a continuation. All we do is we pass this base executor to those functions as well, and those functions ensure that we have the property of that base executor. So based on that, the async execute implementation is really simple. All we need to do now is we simply have to add the call to async replay validate underneath, and it will ensure that we have the resilience properties. Similarly, to handle bulk way async, bulk way execution, we need to implement a bulk async execute policy. Now, this is not as trivial as it was with the async execute policy. So I do not really want to go into the detail of why we do it this way. All we need to emphasize on is line number 11, wherein we have a bunch of results, a vector of futures, and based on that, we spawn hierarchically these results. And somewhere within the spawn hierarchical, all we do is we increment the result within the vector, and all of them call the task async execute. So as I alluded to in the previous slides, I told that bulk two-way execution or the bulk async execute method is nothing but async execute just made bulk. That's essentially the whole idea over here as well. We have a bunch of results this time, and each of those results actually spawns another async execute, and that's how we have the whole idea of asynchrony and resiliency within the executor. And overall, all we need to do now in terms of code is we need to have a base executor. Over here, I chose a parallel executor within HPX. You can actually choose any of the executor. It need not be an HPX executor either. It could be a sequence executor. It could be your own defined executor that has thread pools. All it needs to make sure is it needs to have an implementation of async execute and bulk async execute. So when we create this replay executor, since these two, the above base executor has async execute and bulk async execute, things will work for the replay executor as well. And in terms of usage, it is really easy. All you need to do is you need to pass this executor to the async method if you want to have an asynchronous call, and if you want resiliency over that asynchronous call, if you want to invoke a task asynchronously and you want resiliency, all you do is you pass that executor. Similarly, if you have an algorithm that takes a bunch of argument, all you need to do now is you need to pass that executor to that argument, and somewhere within the implementation of that algorithm, you need to just use the CPO to ensure that you execute the algorithm within the execution resource. And similarly, if you have a bulk execution system, for example, a for each, you need to pass in the executor to the execution policy, and you will have the property of resilience executor. And the things that I want to emphasize here on is that there's virtually no effort on the user side. And this is actually really, really important, because in the high performance computing space, we have code bases that are millions of lines of code. And if you want to add resilience just because you want to simulate those applications on large scale supercomputers, you do not want to go through each line of code and add resiliency in there. So This way, we have a method of search and replace, sort of, wherein we go into every file, we do a search and replace, and we simply add executor as an argument to the method. And all of those methods will all of a sudden have the property of resilience. So it's virtually no effort on the user side. Next is its clean and readable code. Since resiliency overall is a property of an executor, property of an algorithm, and not the algorithm itself, what happens is you actually lose readability if you use those async replay variations instead of the executors. With executors, instead, it comes up as a property, and therefore it's very clean and it's very much readable. And in the end, it's composable as well, because you pass in that executor to that algorithm, and like things simply work for you. And based on composability, I need to emphasize on a few points. First is that resilience executors are base executor unaware. So as I just said, you can have a parallel executor, you can have a sequence executor, you can have any other executor as long as it supports async execute and bulk async execute policies. Things will work for you. So resilience executors are base executor unaware. That's one level of generic algorithm. Next is resilience executors are algorithm unaware as well. You can pass it to any algorithm, and as long as that algorithm supports executor, that is, it knows how to call the CPO for that executor, things will work for you. And therefore, resilience executors are also algorithm unaware. And finally, the most important one for our scenario is that resilience executors are runtime unaware as well. So for example, Cocos is another runtime written in C++ that works on heterogeneous computing. It works on GPUs, it works for CPUs, and it supports a variety of memory hierarchies. Now, Cocos also has execution spaces, and based on that, we implemented the HPX Cocos executors, a layer between Cocos and HPX. And based on that layer of HPX Cocos, we actually implemented the HPX Cocos resilience. So for example, if you go through to this code, we have the default host executor, which is an executor that runs on CPUs. And based on this, if we create this replay executor that takes this base executor, we need to understand that the code written inside of this base executor and inside of this replay executor is an implementation within Cocos. It has nothing to do with HPX. It uses Cocos parallel for and other Cocos primitives. But since it's an executor and it supports all those policies that HPX does, we can actually pass it between inside of HPX, and we will have things working. This HPX async call is implemented within the HPX implemented API, and yet it still works. Things just work, and that is the whole idea behind the implementation, is that executors lead to readable and composable APIs. And that's my talk. Thanks a lot. If there are any questions, I'd like to take them right now. Okay, so seems like there are no questions. Thank you, Ren. And if you have any questions, if you want to discuss on resilience of executors, I'll be available in the virtual venue throughout the day. So you can just ping me there and I'll be able to help you with the talk. Thanks a lot.